Good morning, and thank you for having me at this for this conference today. I think that this is a really timely, a good time to be having meetings like this. I think space resources as a topic is something which is going to grow in prominence substantially in the next few years. And I think it's great that the initiatives are being taken like this to create these kinds of meetings and create good links between research, science, industry, and innovation, preparing us for the future of space resource utilization, which could be something enormous. And at the very least, it's going to create a lot of new innovations and new ideas that are going to benefit us here on Earth. What I would like to do in this presentation is, as we're opening the conference, to give what I think is a fairly high-level overview of what space resources utilization can encompass, what some of the key opportunities are, and also some of the challenges that are coming. For those who don't know me, my name is James Carpenter. I'm from the Directorate of Human and Robotic Exploration at the European Space Agency. There I'm the discipline lead for planetary sciences and moon utilization manager, looking at the scope of things that we would plan to do on the lunar surface for science, technology, and the preparation for the use of lunar resources. So I think before we get going, I think the first thing we ought to do is to talk about what's out there. And I've taken here the moon as an example because we are pretty confident the moon is the first place where this is going to happen, where we're going to start using the resources of space. But the products and the resources we're looking at are kind of similar wherever we go. So the first would be propellant. So the red bar on this indicates propellant or fire. So on the moon, we know now that there are areas of permanent darkness and extreme cold, places where water, ice, and other volatile chemistry can become trapped. We have measured now the presence of water ice in these cold regions. And water ice, of course, has the possibility to be both useful for life support systems, but also is hydrogen and oxygen, which can be propellant which can be used to power things from the lunar surface up into lunar orbit, and actually to go from different areas in space to other places, building fuel, creating fuel on something which has a low gravity, and so it's much easier to supply fuel from than the surface of the Earth. The other is water. So water is, of course, useful as a product for life support systems primarily. Actually, it's worth mentioning also that although water ice is where a lot of focus is, the minerals on the moon are around 40% oxygen. And if you can pull the oxygen out of those minerals, then you already have the heaviest part of propellant. So you already have one of the major products of propellant right there. We also know that embedded in the lunar materials from the solar wind, we have hydrogen and other volatiles which could be extracted and used for propellant and other things. Moving around to the right, on the orange, we have metals. So once you've ripped the oxygen out of these minerals, what you're left with is metallic ores, metallic products that could be used for manufacturing. Oxygen, of course, is again useful for life support systems. Moving around again to the green, we have building products in the green. So this is where you would take regolith, the ground up, powdery, fine rocky material that we find on the lunar surface that's been generated by billions of years of meteoroid impacts. We could use that to actually build things on the surface. So we need to be things like landing pads to prevent the throwing up of dust and hazardous material during descent and landing. This could be to prepare radiation shelters, or it could be to create basic structures on the lunar surface. And actually, equivalent, if we're looking at asteroids or other places, we're also looking at similar kinds of products. So these are the kind of things that we're focusing on. What I haven't talked about here actually is energy. And if you like, we already do in space resource utilization through solar power. So solar energy is probably the major resource for Earth, and actually something we already use in situ. So we're already used to that. But this is another thing where I think there's future opportunities for energy in space too. I think some important caveats. There are enormous opportunities in this space resources domain. So if we think about the resources of space and the solar system, there are potential, by current standards, we are almost limitless in what we could conceive of accessing and using. The caveat would be, today, nobody has demonstrated that space resources are useful. So we must be careful to prepare in a way where we manage the risks associated with it. So it's very, very high reward potentially, but also very high risks. So I think that we just have to make some assumptions about what will be useful, when it will be useful, and how it should be accessed. And we need to create the knowledge base that allows us to take good decisions and careful decisions about the way we go forwards. And so we're aware of and manage the risks of investing in this domain. Something I observe is that it is an extremely interesting area. So there's a growing community of people wanting to work in this domain, but there are risks associated with it, and we need to be careful about how we manage those. So we see that there are a number of different potential applications for space resources, and the first of these is going to be for space exploration. So using the resources we find locally to meet the needs of exploration missions. Primarily that's going to be associated with human missions. So the first opportunity we see is the production of propellant to support human surface activities, and then at some point moving into basic structures like landing pads and radiation shelters, and then eventually moving on to metals and things for manufacturing. A challenge of exploration is that the activities associated with exploration are small enough that we are trying to find where is that tipping point where it actually becomes worthwhile doing space resource utilization to meet the needs of exploration. At present, that need is not there, and there's a bit of a chicken and egg thing where if space resources were available, it would increase substantially what was possible through exploration. But it is difficult to invest enough in the initial cost that it takes to bring space resource utilization up to a level of readiness where you can base your exploration systems on it without having the customer that's planning to use it. So nobody can plan to use it until it's there, but nobody will invest in it being there until somebody's planning to use it. And right now, the need is not at the sufficient level to make it worthwhile. So the activities at the moment need to be focused on trying to establish that need and take the steps needed in a consistent way and in a steady way to get to the point where we can use it and we create those opportunities. The second application is going to be for the space economy. Most space resources are going to be used in space. And so the question is, beyond exploration, which is a pretty small market, a pretty small use case, are there space applications that are economically driven and thus much more substantial that would benefit substantially or are enabled by space resources? So there are certainly models out there to show that propellants made on the moon or asteroids could potentially be used to supply orbit raising for geostationary satellites, for example, to go from orbit to geostationary orbit. And maybe there are use cases associated with that. I would still argue that's a fairly small market, and so nothing really has been demonstrated yet. One application that I think I at least see coming with substantial interest, certainly in China and in the US, and we see things rising now in Europe too, is the use of space solar power. So space solar power is something that's been postulated since the 1960s as a way of providing clean energy to Earth. So the idea is you create very, very large spacecraft, probably in geostationary Earth orbit. They collect solar energy and then beam that energy, probably using microwaves, down to ground stations on Earth. And there's a lot of literature out there that you can look into. And initially, these power stations, it could be on the same scale and for equivalent cost to nuclear, for example, would be built entirely using terrestrial materials launched into space. In the future, those power stations, if that were a capability that was scaled up, would require large amounts of propellant for station keeping, materials and other things for manufacturing. and you could, or for maintenance. And you could also consider that the very large structures, we're talking about many square kilometers of collecting surface, for example, those could be sourced and manufactured in space and supplied to these power stations. If this were realized, this is an application that would be so substantial compared to what we do in space today that it would really merit probably the investment in space resources. So this is the kind of thing that I think could be a game changer for space resource utilization if it became part of the planning for part of a balanced energy portfolio. And certainly we see China and Japan have this as a very clear objective. There's been a lot of work done in the past in the US and some in Europe too. And let's see whether this becomes part of the energy balance that we're looking for the future century. And finally, there are applications for Earth. So this is an illustration that comes from a report produced by the Luxembourg Space Agency with PricewaterhouseCoopers, looking at the future applications. This is, I think, the Luxembourg Space Resources Strategy this appears in, talking about the different products and when they might appear. And so here you see that the return of things for Earth comes quite late. So really, in terms of these platinum group metals, is one of the main things that they perceive as being useful for Earth. So certainly there's not much of a market for water on Earth. So I think one thing that is not clear today is what, if anything, that you could harvest in space is of sufficient value to merit its return to Earth. And so take the platinum group metals for an example. There's a book by a guy called Dennis Wingo called Moonrush, where he describes the use of platinum group metals in catalysts for fuel cells. And the idea that platinum group metals, if sourced in space, could be sourced at such a substantial level that they would destroy, it would really lower the cost of platinum group metals on Earth, and thus improve the economic viability of the hydrogen economy, for example. So there are a lot of assertions out there about things that could happen in the future. Some of those need testing. But at the moment, I think huge uncertainty about what the future might hold for Earth and benefiting Earth directly in terms of returning things to Earth. Although things like space solar power, for example, would of course be useful for Earth straight away. So the big question we have is, and this is that underlies all, I think should underlie the majority of what we're trying to do in space resources as a domain today, is the question, are space resources reserves? So if you think about resources, these are potentially valuable with reasonable prospects for eventual economic extraction. So when we talk about space resources, that is what we mean. A reserve would be something that is valuable and legally, economically, and technically feasible to extract. And today, we do not know whether any resources in space are reserves. And so the big challenge for us in this very early phase of space resource utilization is to answer that question, to identify the resources and say, are they or are they not reserves? And so actually starting to happen towards this, but I would say it is not being done internationally in a really planned step-by-step way, but there is a certain logic to what is happening, which is going in this direction. And if you think about lunar polar ice, we know now that it's there, but we do not know, for example, whether the abundance of water ice, its distribution, whether it's just associated with permanently dark places or whether it can be in other places too. We don't know how accessible it is. We don't know its origins or the geologic processes that put it where it is. And so if we want to understand whether lunar polar ice, for example, is a reserve, or if there are reserves there, the first thing we have to do is to understand what is there better. So to do that, we would need a campaign of activity. So the first thing you need to do is to use orbital data sets to get a global view of what's there. And so what you see below, for example, is a model of water ice distribution produced by a group at the University of Oxford in the UK based on diviner data from the NASA Lunar Reconnaissance Orbiter. And that shows where ice could exist within a meter of the surface at the lunar south pole based on temperature data measured from orbit. We then need to provide ground truth with lots of comparable measurements at different locations. At the moment, we have ground truth or semi-ground truth in one location, which is in a permanently dark crater called Cabeus, where in 2009 the L-Cross mission slammed into the surface with an impactor, threw up a plume of material that was then measured by other spacecraft. And that plume of material contained a number of volatile chemicals, including water. And so we know that water is there. That was the first confirmation of the hypothesis that water was at the surface of the moon at the South Pole. So now we know it's there. Now we need to go and investigate that to understand it better. So what we need now are more comprehensive and capable in situ measurements at different and diverse locations at the surface, with comparable measurements to measure what is there in different environments and in different places. This will allow us to create data sets we integrate to create a geological model of water, ice, and volatile distribution at the lunar poles, which allows us to then assert, well, this is where we think a reserve would be. This is somewhere we would like to go based on our geological model. Then we need to send a very capable mission to that location to map and understand the ice distribution across the surface and the subsurface at that location, and then report on the ore body. And at that point, we then confirm this is a reserve. Now, that's a very substantial thing. It involves a lot of surface activity, a lot of missions, and actually an international polar resources campaign is happening. It's already started. So if you think of L-Cross being the first one, now we have NASA have the Viper rover, which is planning to go there in a couple of years. We have the Prime 1, which is a drilling instrument from NASA going with a commercial lander, I think either 22 or 23. We have Japanese missions, we have Russian missions, we have Chinese missions, all planning to go and explore this region. And while ESA doesn't have its own mission, we are deeply involved in a number of these missions as a partner. And the core product we're using to participate in this campaign is something called Prospect. So this is an image of Prospect on the Russian Luna 27 lander, which is planned for 2025. So Prospect is this drill. This is the silver drill that you see there. This will drill up to a meter beneath the surface. It will extract samples, deposit those samples into a comprehensive chemical laboratory, which will then heat up the samples, measure the water, ice, and other volatile chemistry that comes off those samples, and then measure the composition of what comes off, and also the isotopes to understand the origins and geology of those volatiles. We can also perform some experiments with this laboratory into different oxygen extraction, reduction process experiments by introducing hydrogen and other chemicals into the crucibles that we're using to heat up the samples. This is a very smart piece of kit, which we're contributing to Luna 27, but we're also contributing with Prospect and its derivatives to other missions. So the first sort of derivative of Prospect is actually flying not to the poles, but the first mission for what we call the ion trap mass spectrometer. Part of the instruments that are inside this lab is being flown to the moon on one of the first NASA commercial missions with a company called Astrobotic next year in 2022. And on the right-hand side of this image, you can see the integrated flight hardware for that instrument, which will be measuring the exosphere, the locally produced atmosphere by the lander, and then the natural tenuous atmosphere of the moon at the lunar surface, not at the poles, but as a to use for science, but also to demonstrate and prepare the capability for later. We also then plan to fly that same instrument as part of the JAXA ISRO Japanese Indian rover mission to the lunar South Pole, which they're planning for 2024 or 25. This would be part of a package which would again be looking to investigate water, ice, and other volatiles close to the surface. And then we're providing the full Prospect package, drill, and the full laboratory to both a NASA commercial delivery planned for 2025 and to the Luna 27 mission with Roscosmos also in 2025. So this is our contribution to I think what is a very substantial international campaign. And of course, the Artemis program with humans from the United States is also focusing on the lunar South Polar region as the location for future human missions to the moon. And then the next step is going to be, once you've been to all these different locations with all these different missions and you have this ground truth, you need to go somewhere where you think there's water ice and explore in more detail. And for this, we are studying a mission. So this is no decision is taken at this point on whether to implement this mission, but we are studying a mission called Polar Explorer. And Polar Explorer would be a mission which is sent to the moon in the early 2030s, most likely, and would be landed on the European Large Lunar Lander, or EL3, which is in development at the moment. This lunar lander can deliver around 1.5 tons of payload to the lunar surface. And in the Polar Explorer study, this includes a very capable rover to map a region where we think that water ice would be present in an economic level, and also an assortment of other instrumentation to understand the broader environment at this location. And the EL3 can also be used to deliver cargo for the early Artemis missions. And so and you see just an astronaut here to give you an idea of scale for the lander. We're also looking into the processes and technologies that you might apply, not just at the poles, but anywhere on the moon. And so another thing that's really important is to look at how to extract oxygen and create metals and from lunar materials. So this is just an image showing the outcomes of one of the experiments that we've been involved with, where lunar simulant material on the left is reduced into a metallic ore on the right-hand side. So we have processes now that we can use, electrochemical processes, to pull all of the oxygen out of pretty much any rocky material. What we're trying to understand now is whether or not these can be applied at the moon, and also how we can tweak these processes to provide a process that is really applicable at the lunar surface and with lunar materials. Initially to produce oxygen, but then eventually you would be wanting to produce these metallic materials, metallic powders too. And one of the key things will be to demonstrate that that's actually credible and feasible. And so for that, we've been preparing an in situ demonstration mission. This is something which is currently in phase B1. And this would be a mission to demonstrate the production of oxygen and metallic residues on the surface of the moon using lunar materials at a subscale. So we'll be looking at hundreds of grams, that kind of order of size of the batches that we would be reducing with this equipment. And so that's something which is ongoing at the moment. We would scoop up material from the surface, insert it into our reactors, reduce the material to pull all the oxygen out, quantify the oxygen we've produced, and then investigate the metallic powders to understand what their properties are afterwards. So this is both a demonstration, but we also plan to do scientific experiments with this equipment to understand better the processes that we're developing on Earth. We also are working on those processes on Earth, and most of the work on ISRU has to happen on Earth. But there will be very specific things that need to be demonstrated on the lunar surface or tested on the lunar surface. And so we need to try and find ways that we can focus our efforts on the moon to the things we have to do there in order to prepare. The approach would be to go from having our terrestrial activities to have a demonstration to test critical things, but also to show it's possible at the moon to kind of break that chicken and egg thing. So we demonstrated it can be done. And then move on to a pilot plant sometime during the 2030s. And then to eventual in situ resource utilization sometime after that. So these are things that are all kind of in preparation at the moment. Decisions on the full development of some of these things will be taking place at the end of 2022 at our next Ministerial Council meeting. So those are some of the things that we are doing, kind of the scope for them. I think it's useful maybe when we think about space resource utilization to consider this in the context of the whole. And so working with a scientific topical team that we've established, we put together this thing, which is called the Universal Flow Sheet. And if you look for this, there's a paper was published in Planetary and Space Science describing this and the nomenclature associated with it. And it basically describes for any given resource, what is the flow of activity that needs to happen in order to produce products and waste, and what is associated with each of those. And so just in this chart, I just wanted to indicate the focuses for research and development in each of these different areas associated with different resource extractions. So we need to understand what's there. We need to understand the environment, its effects. That's really a planetary science question. Like, what is there and what's it like? What are the implications of that for the process we want to undertake? Then we need, in terms of excavation, we need to make sure we're targeting the ore and avoiding the gang. We want to optimize energy efficiency, minimize environmental impact, and understand the interaction to this environment. Then we need to understand what beneficiation is needed to process these ores. How do we handle big finds, small finds, big particles? Again, energy mineralization, maximizing enrichment ratio and efficiency, and zero water. And then in terms of the extraction, we need to look at the different processes that might be applied. We want to maximize the yield, maximize the conversion, and minimize the energy. And there are three things in this that are really useful because they're also massively driving for terrestrial resources in the future. One is autonomy, which is something that is very difficult terrestrially, has not been mastered, and makes it to be a big challenge for space, but something that we're going to need to work on. Energy efficiency and zero water. So these are things that are really useful as targets because there are big spin-out opportunities into terrestrial resource industries, providing some real terrestrial benefits soon. And finally, a lot of this you will find in the ESA Space Resources Strategy, which is online. This is the URL, or just Google ESA Space Resources Strategy, and you'll find this document, which we produced in 2019, I think, which describes basically what we in ESA are aiming to do in the area of space resources. And this is something which we aim to update every few years, and so we're currently involved in consultations to understand what about this and the assumptions you made in it are continue to be valid, and where we may need to make changes or updates, because this is a very fast-moving field, a lot of activity on Earth and in space, and we want to make sure that it remains current and provides good guidance for us, but also the broader community in Europe about where we might want to focus our efforts as a community who would really like to see this happen. So that's everything for me. Thank you for your attention, and good luck with the rest of the conference. Thank you.